All right, so welcome back to another Math 231 GSG session. Today's session will be covering, chapter 13 from the textbook. All right, so before I get started, for those of you guys who are in this call right now, can you please type down your PSU ID, the one you used to sign into Canvas, into the chat box? I'll be highly appreciated. All right, and other than that, any questions so far regarding the course and anything? All right, I guess that's no. All right, so let's get started. So let me pull up a whiteboard real quick. All right. So let's start off with 13.1. Oh, let me not use red. Let's use black for this. There you go. All right, so for 13.1, this was an introduction to actually using vector functions, right? So a bit of a recap. So let's say I have R, the vector R of t, which is equal to, let's say, t squared plus 1, comma, t, and comma, 2t plus 1. This in IJK format would be the same thing as t squared plus 1 I hat plus t j hat plus 2t plus 1 k hat, right? Okay, wait, hold up. Let me reformat my screen a bit. Let me make this full screen. All right. So we have something like this. So from this, we can note that, again, this is your x component right here. This is your y component, and this is your z component of the vector. And what you notice about vector functions is that every component, so x is basically a function of t, y is another function of t, say g of t, and finally z is also another function of t, let's say h of t. Right, so this is a bit of a recap. All right, yeah, so any questions off of vector functions? All right, perfect. Let's get straight to the questions then. All right, I'm gonna start off with curves of intersections. So you guys covered this during lecture, and I'll be pulling in examples from the textbook. All right. So looking at the textbook, all right, let's see. So curves of intersection. I have 13.1, number 42. All right, so let's start off with number 42. All right, let's see what 42 has. All right, so let's say we have a cylinder of, let's say, cylinder of x squared plus y squared, which is equal to 4, and we have the surface of z is equal to xy, right? And the goal of this question is, again, to find the curve of intersection and write it down as a vector function. All right. So whenever I'm dealing with these kind of questions, a few things to note is whenever you're dealing with something like an x squared plus y squared, which is equal to a constant, or like whenever you're dealing with two variables with a square. So let me highlight that down. So looking at this first function where you have x squared plus y squared is equal to 4, this is actually gonna tie into the, so let me just write this down. So you're actually going to incorporate this trig identity, sine squared theta, or rather, yeah, sine squared theta plus cos squared theta, which is equal to 1, right? That should be a familiar trig identity. So actually, looking back at this question, we see that we have x squared plus y squared, which is equal to constant. And so we can basically substitute x as a sine theta, y as a cos theta, right? But the only difference between these two is that this function has to equal 1, while this function, or this right here, the cylinder given is x squared plus y squared is equal to 4. So essentially what you're trying to do is you're trying to multiply both sides of the equation, or this equation right here, right? You're essentially just multiplying 4 to both sides. And yeah, there you go. So going back to this equation right here, so I'm gonna write that, from what you guys have covered in lecture, you're gonna be writing most of the vector functions in the variable t. So I'll keep it consistent throughout this session. All right, so looking at this equation right here, we can represent x as sine of t. Let me use black. Sine of t plus cosine, or sine squared of t plus cosine squared of t multiplied by 4, which is equal to 1 multiplied by 4, right? And that's why that works out. And so in this case, you have x equaling to 4 sine of t, or 2, sorry. You have x is equal to 2 sine of t, while y is equal to 2 cosine of t. All right. So whenever you're dealing with these kind of questions where you have two variables and both of them are squared, equal to a constant, you can, and you're summing them up, you can use this trig identity to help condense it down into x is equal to 2 sine t and y is equal to 2 cosine t. All right, because you're trying to rewrite all your variables in terms of the variable t for vector equations. Okay, so any questions so far? All right, perfect. So that is x and y. Now the only missing parameter out of this equation now is your z parameter, or z variable. And shown through this question, z is equal to x multiplied by y. So what you can do is you can take what you solved for, or what you found for x and y, and just basically multiply them together. So we get 4 of sine t multiplied by cosine t. So for this equation, your vector function for the curve of intersection is actually gonna be 2 sine t, comma 2 cosine t, and finally 4 sine t cosine t. All right, and this is gonna be the answer for 42. Okay. And just to recap, the biggest thing what you want to do for these curves of intersection is rewriting each variable x, y, z in terms of the variable t. Okay. All right, let's go through one more question, or two more questions actually. So that's 42. Let's go over 44 from 13.1. So let's say for 44, we have paraboloid of z is equal to x squared minus y squared. And we have the cylinder of x squared plus y squared equaling 1, right? And then same thing, you want to find the vector function of the curve of intersection. All right, so for this question right here, again, you see right here that you can basically treat x as either sine theta or cosine theta and y as cosine theta from the trick basically mentioned in the previous problem, right? And so that's my x and my y. And so since I found my x and y, I can just go back and refer back to this paraboloid equation to figure out what my, or sorry, let me just label it as t for consistency. And yeah, and going back to this paraboloid equation, we can figure out that z is the same thing as sine squared t minus cos squared t, right? And so for this question right here, the curve of intersection is gonna mimic this vector function, where your x component is gonna mimic sine of t, your y component is gonna be portrayed as cosine of t, and finally, z is gonna be the same thing as sine squared t minus cos squared t. Okay. All right, and so that is going to be the answer for this question. All right, so pretty straightforward so far. Yeah, I have one more question dealing with curves of intersections. So let's go on to number 43. Yep, 43. All right. So again, same exact question where you're trying to find the vector function of the curve of intersection. For 43, we're given a cone where z is equal to square root of x squared plus, or yeah, z is equal to square root of x squared plus y squared, and the plane where z is equal to 1 plus y. All right, so for this question, I'm actually going to go through two different solutions or two different methods to get the same answer, basically. All right, so for the first method, I'm actually going to rely on the equation of the plane first. So I'm going to look at the plane equation first. Okay, let me move my screen. All right. So looking at the second equation of the plane equation, I have z is equal to 1 plus y. All right. At least whenever I look at these kind of questions where you have a one variable dependent on another variable and it's linear, what you can do is you can treat one of the variables. So let's say I'm going to treat y. I'm going to look at y, and what I can do is I can set y is equal to t, right? And so from that, since z is dependent on y, z is actually going to be the same thing as 1 plus t. So just from the plane equation, I can actually formulate both the y component and the z component of the curve of intersection. All right, so I have the y and z. The only thing I'm missing is the x, right? And that's when I'm going to refer back to my first equation. So the cone equation, sorry. So I'm going to refer these two up here and single out for x, basically. So let's plug it in. So for z, I have 1 plus t, and that is equal to the square root of x squared, right? We're trying to figure out what x is, plus y squared, which is basically just t squared. And so single out for x, I get 1 plus t squared, which is equal to x squared plus t squared. And so it'll be 1t squared minus 2t, or plus 2t plus 1, which is equal to x squared plus t. And so x squared, or x, is equal to the square root of 2t plus 1. All right, so we have these three parametric equations for my vector function. So that's using method 1, right? And this is the key from method 1. I guess that's like, yeah, the most important thing throughout this question. Okay. And then for method 2, another way of solving this question is actually, you notice that these two functions are set equal to just z, right? So what you can do is you can actually set these two functions, so square root of x squared plus y squared, and set that equal to 1 plus y, because both of them have to be equal to z, right? And so from that, what you can do is you can single out for you can single out for y, or expand this out. Let's see. So I can square both sides, x squared plus y squared, which is equal to, y squared plus 2y plus 1. And what you can do is you can single out for one of the variables. So from this, these y squares cancel out, and you're left with 2y plus 1 is equal to x squared. And so I'm going to single out for y in this case. Okay, you can single out for x, feel free to do so. But I basically get y is equal to x squared minus 1 over 2, right? So again, what I can do for this question is I can use the same exact thing I used over here, right? I can set my x into t, right? So instead of setting y equals to t like in the first method, I can just set x equals t after condensing it down to this equation. And after condensing x, or setting x is equal to t, then I can find the parametric equation for y as y is equal to t squared minus 1 over 2. So from that, I get both the x equation, or x function, and the y function. Okay. All right, so that's x, that's y, and the only thing I'm missing is the z. And for z, I can use either the cone equation or I can use the plane equation. I'll just use the plane equation because it's easier, looks easier. So z is the same thing as 1 plus t squared minus 1 over 2, right? So simplifying that down, I get t squared plus 1 over 2. All right, so these are my parametric functions, solving it this way. Okay. All right, any questions so far? All right, now I have a question. So what do you notice about the parametric functions between solving it the first method and the second method? What do you notice about the x here and the x here? See, something to note out is that the functions in terms of t is actually not the same. Using the second approach, we get that x is equal to t, right? While using the first approach, we get x is equal to square root 2t plus 1. But if I were to graph it out, so if I were to show you using GeoGebra, let me see if I can show you. All right, let me share my. All right, so using GeoGebra, let's try to graph out the two equations we solved for. So we have, using the first approach, we have curve of, so for the x component, we got the square root of 1 plus 2t, right? Now for the y component, we have t, just t, and for z, we have 1 plus t. Yes, I should have that, and then we're gonna do it in terms of t, and let's put the range in between. Let's say, well, it can't be it can't be less than negative 0.5, right? Because you can only have you have to make sure that anything under a radical is greater than 0 or equal to 0. So let's do negative 0.3. Let's go up to 5. Start off with that. All right. So first of all, do you guys see the curve on the screen? Yes, hopefully. Yeah, I'm not too sure if, okay, perfect. Yep, someone said yes, it's good. All right, so that is solving the curve using the first approach. Now, using the second approach, we have the curve. So for x, we actually have t. For y, we have t squared minus 1. Oh, t squared minus 1 divided by 2. And for z, we have 1 plus t squared. Let me use t squared plus 1 all over 2. Let's say we're using t. Let's say we're going from, well, in this case, domain doesn't matter. Let's just use the same interval. So from negative 0.3 to 5. Right? Let me change the color of this curve. So let's make it green. Okay. There you go. Okay. All right. And you see, two curves are basically identical, right? So it's just, these two curves are referring exactly to the same graph. So either approach should work. Yeah. All right. All right. So any questions on that? All right, let's go to the next question. So I think that is all from 13.1. Yeah, 13.1 is just basically an introduction to just vector functions. Do you guys have any questions you want me to cover from 13.1, or can we move on to 13.2? All right, I'm going to take that as no questions. So let's go to 13.2. All right. All right, so 13.2 is applying derivatives and integrals to vector functions. So yeah, I'm gonna dive into questions. I have a few questions I've prepared. This is again from the textbook, so feel free to refer to that. All right, let's start off with number 23. Okay, so 13.2, number 23. All right, let's see what number 23 says. Okay, so for number 23, they gave us parametric equations or parametric functions where x is equal to t squared plus 1, y is equal to 4 square root of t, and z is equal to e to the power of t squared minus t. And they gave us a point. So let's say point at 2, 4, 1. And the question is basically asking to find, so find parametric equations for the tangent line to the curve with the given parametric equations at the specified point. All right, so you're basically trying to find the tangent line from these constraints they give us. All right, so let's see how we, all right, so let me use red. Okay, the question is find tangent line. Okay. So from our discussion with lines, we need two things to form a line. First thing we need is we need a point, all right? And the second thing we need to form a line, just a line in general, is we need a directional vector. Okay. All right. So for this question, we are given a point. So that's a check. Only thing we need to find is the directional vector. And that's where we utilize this idea of deriving deriving the vector functions, right? Okay, hold up. All right, so we have, okay, I'm just gonna rewrite this in vector notation. Let's say we have R of t as t squared plus 1, comma, 4 square root t, comma, e t squared minus t, right? So just like how we find tangent lines in Calc 1 and 2, it's kind of the same idea. The first thing we need to know is we need to know the tangent vector, right? And the tangent vector is basically the derivative of this displacement, or this r of t, this vector function right here. So deriving this, we essentially get the gradient of each component, right? We get 2t for the x. We get, what is it? T to the negative 1/2 of 2. And we get et squared minus t multiplied by 2t minus 1 for the z component, right? So this is basically the gradient, and dx, that's basically dx over dt, that's basically dy over dt, and that's basically dz over dt. That's how I usually think of it. All right, so we have dx over dt, dy over dt, and dz over dt. Now we're trying to find the tangent line, right? At a specific point that we're given right here. P, this point at 2, 4, 1, right? So we need to find the slope of x at a specific time, slope of y at a specific time, and slope of z at a specific time. So one thing we need to also figure out is, let me just actually add it on to this list right here. Okay. The third thing we actually need is we need to classify what our value for t is. Since in this question, they don't give us the value for t. What we can do is we can take this point right here, and we can set each respective component to our parametric functions. So at this point, 2, 4, 1, since we know this point has to be in the vector, right? In the vector function, we can just set 2 is equal to t squared plus 1. And so t has to be equal to 1, right? And we can just verify if t equals to 1 works with both y and z. So if y is equal to 4 of square root of 1, that's the same thing as 4. And that matches off with this point right there, right? And so for z, again, same thing, e to the power of 0 is equal to 1. That matches with that, right? So our t value is going to be 1. Okay. All right, so let's find our gradients at that specific time. So we find r prime of 1, which is going to be 2, right? 2, and let me see, e to the power of 0, which is 1, and then 1, which is 1. Should be it. Let's see what I got. Yeah, 2, 2, 1. All right, so this is basically a directional vector at that point for the tangent line. And so, let me highlight all the important aspects for forming the tangent line. So let's say trying to form a tangent line. So let's say I have R, let me represent as T. This representing my tangent line. RT is basically, T is basically my point plus 2t, comma, my point at y, which is 4, plus 2t, and z, which is 1 plus t. There you go. If I write this in parametric equations, it'll be x is equal to 2 plus 2t, y is equal to 4 plus 2t, and z is equal to 1 plus t. All right. So again, this right here, that's basically that right there. Okay, so that is number 23. Okay. All right, let's move on to the next question. Let's go over 26 now. Okay, so 26 is the same exact list. This is the same exact question, just different parametric functions. For 26, we have x is equal to the square root of t squared plus 3. And then we have y is equal to ln of t squared plus 3, and z is equal to t, right? And we have the point 2, comma, ln 4, comma, 1. So I'll start by actually finding my value for t. So we can, based off these equations right here, we can say that square root of t squared plus 3 is equal to 2. And so t squared plus 3 is equal to 4, and hence t is equal to 1. And it works out for y and works out for z. All right, so we have the value for t. We have our point right here, 2, comma, ln 4 and 1. And the last thing we need is our directional vector. So r prime t is going to be the same thing as t squared plus 3, power of negative 1/2, multiplied by 2t. We have 1 over t squared plus 3, multiplied by 2t. Finally, we have 1 for z, right? And then plugging in t is equal to 1, we get the gradient for the x component as 1 plus 3, so that's 4, right? So that's 4 to the power of negative 1/2, multiplied by 2, comma, 1 over 4, multiplied by 2, and we have 1 for z. So that equals, what's that, 2 over 2, which is 1, 1/2, and 1. Okay, let me just double check that. 1/2. All right. Yeah. Should be it. I'm missing something. Oh, I'm missing something. This derivative is not exactly right. That's where it seemed off. All right, so that's actually 1/2 right there. I'm missing 1/2 right there. Okay, so this is actually gonna be 1 over 2. All right, so my tangent line is actually gonna be, so for my answer, let's see, it's just eraser. Is this? So for my tangent line, my parametric functions are gonna be x is equal to 2 plus 1/2 t, y is equal to ln of 4 plus 1/2 t, and z is equal to 1 plus t. There you go. And that's going to be my tangent line. All right. And yeah, that incorporates the idea of derivatives. Okay. That's the first half of 13.2. Now let's go over another question. Now, this question is actually going to be dealing with unit tangent vectors. So far we've covered how to find tangent vectors, which is just basically this right here. This is basically classified as a tangent vector. Okay, that's my tangent vector. Tangent vector. Now, incorporating the idea of unit vectors back in the previous chapter, in 13.2, they introduce you to t of t, which is the unit tangent vector, which is essentially just r of t, or r prime of t, all over the magnitude of r prime of t, right? Since dividing it by its magnitude will result t of t, the magnitude of t of t, to be just equal to 1. And so from this, we can say that the magnitude of t has to be equal to 1. This should have been covered in lecture. Okay, so let's go through an example. So let's say we have r of t is equal to cosine t I hat plus 3t j hat plus 2 sine of 2t k hat. And let's say we're trying to find the unit tangent vector at time is equal to 0. Okay. So this is given in the question, this part. Okay. So I'm going to start off by finding what r prime of t is. And so in this case, r prime of t is going to be negative sine t I hat plus 3 j hat plus, what was that, 2, so 4 cosine of 2t k hat, right? And r prime of t, the magnitude of r prime of t is going to be the square root of sine squared t plus 9 plus 16 cosine squared of 2t, right? And so adding, dividing the r prime t with the magnitude of r prime t, we get t of t, the unit tangent vector, as negative sine of t I hat plus 3 j hat plus 4 cosine 2t k hat, all over this magnitude, which is the square root of sine squared t plus 9 plus 16 cosine squared 2t. All right. And then it tells us that we're trying to find the unit tangent vector at time is equal to 0. So let's plug that in. The t of 0 is the same thing as, so this first term becomes a 0. So there's nothing in the x component. 3 stays as is. And then it's going to be a 4 for the z component. That's all over. Again, the sine term becomes a 0. That's going to be a 9 plus a 16. So if you simplify this down, we get 3 j hat plus 4 k hat all over square root of 25, which is the same thing as this. All right, so any questions from that code? All right, so that's unit tangent vector. I think that's the, yeah, okay. Yeah, I think we're pretty much done with derivatives of vector functions. Let's see if there are any other questions. Actually, let's go over one question. Yeah, I didn't have this planned, but let's go over number 33. This is slightly different from the other questions. So for number 33, let's see, let me read this. The curves R1 and R2 intersect at the origin. Find their angle of intersection, correct to the nearest degree. All right, so we have R1 of t equaling t comma t squared comma t cubed, and we have r2 of t equaling sine t sine of 2t comma t. And it tells us that these two lines, these two curves basically intersect. So they intersect at the origin, which is the same thing as the point 0, 0, 0. And what they're trying to tell us, or what they tell us to do is they're trying to ask us what the angle of intersection is. So we're trying to find the angle of intersection between these two curves. Right, so that's the question right there, angle of intersection. All right, so let's see. So for this question, what you need to know is you need a directional, or you need the tangent vector for these two R1 and R2 curves. So the first thing I would do is I would start off by finding the tangent curve, which is going to be 1 comma t comma or 2t comma 3t squared for R1, and the tangent curve is going to be cosine of t to cosine of 2t comma 1 for the second curve. Right, so these are my tangent vectors. Or tangent vectors for the two curves. All right, so with the tangent vectors, they basically mimic where the line is approaching towards, right? So where the curve is going, basically. And so what we can do is we can find the tangent vectors at this specific point. So we know that these two curves intersect at 0, 0, 0, right? So what we can do is we can find the tangent vector at 0, 0, 0, or where time is equal to 0, right? Because we know that at point 0, 0, 0, R1 has to have a time of 0, right? So because the x component is 0 and t is equal to 0, hence t is equal to 0, right? For R2 of t, we have sine t equaling to 0. So for R2 of t, we have sine of t equaling to 0. And in this case, yeah, it's possible for t equals to 0. Yes, because again, that's the x component. For the y component, sine 2t has to be equal to 0. And when t is equal to 0, that's a valid point. And for the z component, t has to be equal to 0. So time equal to 0 is actually a valid time for both R1 and R2. Okay, so what we can do with that time, so let me just erase this real quick. What I can do with this time is I can find the tangent vector for both R1 and R2 at time equals to 0. So at R1, my tangent vector is going to be 1, 0, 0. And then R2, my tangent vector is going to be 1, 2, and 1. All right. So we basically have two vectors and intersecting a point. And how do we find the angle between two curves? Or yeah, how do we find the angle between two curves? It's basically just a dot product. So what we can do is we can dot R1 with R2. Again, this should be a review from the previous chapter with dot products. R1 dot R2 is the same thing as the magnitude of R1 and the magnitude of R2 and cosine theta, right? Remembering from R1 dot R2, that's the same thing as 1 plus 0 plus 0, which is equal to the magnitude of R1 is going to be the square root of 1, right? So that should just be 1, and R2 is going to be the square root of 1 plus 4 plus 1 cosine theta. And so cosine theta is equal to 1 over square root of 6. And hence theta is equal to our cosine of 1 over square root of 6. Okay. All right, yeah, I think we'll move on to integrals now of vector functions. All right. Okay, so let's go over 41. So for 41, again, from chapter 13.2, on 41, we have so they give us R prime of t, which is equal to 2ti plus 3t squared j plus the square root t of k hat. And they give us R of 1, remember, which is equal to I hat plus j hat. And then the question is telling us to find what R of t is. Okay. So what we can do is we can take this, this R prime t and we can integrate it, right? So we can integrate 2ti plus 3t squared j hat plus square root of t k hat. all in terms of dt. All right. We're integrating in terms of t. So in this case, we get, for the I component, we get t squared plus t cubed. So that's for the I component. It's gonna be t cubed for the j component. It's gonna be a t3/2 and 2/3 for the k component. Right? And since this is an indefinite integral, we're gonna have to add this with a vector, a constant vector c. And that's why they specify in the question that r of 1 is equal to I plus j. Okay, so let's see if you can use this. So again, this represents r of t, and this represents r of t. Okay. So let's look at this. So when r of t is equal, or r of 1, or when t is equal to 1, we have I plus j, and that's supposedly equal to I hat plus j hat plus 2/3 k hat plus c. Right? So what we notice is that the i's and the j's actually cancel out, and we're left with the vector c. The constant vector c is equal to negative 2/3 k hat. Okay, so that's our constant vector. Okay. So rewriting r of t, the vector function is going to be t squared I hat plus t cubed j hat plus 2/3 t3/2 k hat minus 2/3 k hat. Okay. And again, you can group these two into one factor if you wish, but yes, that is going to be the answer for 41. Okay. All right. Any questions so far involving integrals? Okay. All right. Let's see how much time we have. Okay, we have 10 minutes. So yes, that's basically the end of 13.2, the big concepts from 13.2. So now I'm going to go over 13.3, which is arc length and curvature. So for 13.3, I'll start off with arc length, or let's start off with the length of a curve. Okay, I'll start off with that. So yeah, in this chapter, you guys covered how to find the length of a curve, right? Which is defined as L is equal to the integral of a to b of r t, the r prime t, absolute value of r prime t, times dt, where t is in between a and b. Right. So let's look at this for a bit. So let's say, so yeah, this should be familiar for those of you who've taken 211, but I think of this as kind of like, so I would start by representing r of t as a position vector. Okay. So if I were to say that r of t was a position vector, r prime of t would have to be my velocity vector, right? So I'm going to look at this equation through a physics standpoint. So the magnitude of velocity would just basically equal to its speed, right? And since you're multiplying by a time interval, right, it's basically a change in time. Speed times change in time is basically equal to, these two multiply. That basically equals to a length or a distance. Right? So that's basically how this this equation is formed, right? Length and distance. And the reason why it's an integral is because what the integral basically does is it sums up all your lengths and distances at each specific time, right? And yeah, that's basically it, right? Okay, so let's go through an example. So let's go over number 7 in the textbook. So for number 7, they give us r of t is equal to 4 sine t I hat minus 2 cosine t j hat. And it tells us that time is equal to 3 pi over 4. All right. So for this equation, for this question, or wait, no, that's 13.2. Sorry, give me a minute. Not 13.3. Okay, that makes more sense. Let me clear this out. Let's see, number 7. Okay, that makes so much more sense. They give us r of t is equal to t squared, comma t cubed, comma t4, power 4. And the time interval is in between 0 and 2. All right, and we're trying to find the length of the curve, basically, in between 0 and 2. So again, using the formula, we have a lower bound of 0, upper bound of 2, and we're integrating this vector. So I'm just going to represent this in IJK format. It's going to be something like this. K hat. And everything is integrated in terms of time, all right, or dt. Okay, so integrating this, I get 1/3 t cubed I hat plus 1/4 t fourth j hat plus 1/5 t fifth k hat. And you're basically evaluating this from 0 to 2. So evaluating that, I get 1/3 times, times 2 cubed. 2 minus, let's do this. Let's just do it in one go. So it'll be 2 minus 0 cubed I hat plus 1/4 2 minus 0 power 4 j hat plus 1/5 2 minus 0 5 k hat. Okay. Oh, sorry. Yeah, completely missed it. Okay. Sorry about that. All right, I missed the biggest thing from this question. So yeah, I'm still left with the vector. All right, I'm sorry, let me erase all this. So what you're actually supposed to do is you're supposed to find the magnitude first before deriving this. That's a mistake I made. So you want to find the magnitude of r prime t, and it's not r of t. So I'm just going to erase this, the whole thing. Yeah, that's why it didn't make sense. All right, that makes more sense. All right, so using the formula again, I'm just going to rewrite the formula. 0/2 of r prime t, absolute value dt. So let me start off by finding r prime t, which is going to be 2t, 3t squared, and 4t cubed. Right. Finding the magnitude of r prime t is going to give me square root of 4t squared plus 9t fourths plus 16t sixths. All right, so what we're basically doing is we're integrating this. And so integrating this will give me from 0 to 2 of the square root of 4t squared plus 9t fourths plus 16t sixths. All right. And for the purpose of this, from the textbook, it says use a calculator to approximate the integral. So yeah, this will be a really rough integral, but let's try and see if we can condense this down. What we can do is we can simplify this root radical into t square root of 4 plus 9t squared plus 16t fourths. That's one way of simplifying it down. But yeah, you would have to use a calculator. This is a messy integral to deal with. Okay, I have another example where we'll actually go through it. Okay, But yeah, any questions regarding the setup? No. All right. Okay. So let's see. Let's look at the question I actually had prepared. So let's say we're given a vector function RT following this format. And let's say my time interval is from 0 till 2, right? And we're trying to find this length of this curve. So I'm going to present this as R of t. Okay, so let's start off with finding again the derivative of RT, which is going to be square root of 2, comma e of t, negative e power negative t. Okay, and then the next thing I want to do is find the magnitude of R prime t. So that'll be the square root of 2 plus e to the power of 2t plus e to the power of negative 2t. Right? Yeah, and for this one, yes, you can actually factor this down. What you can see from this is e to the t times e to the t gives me e to the power of 2t, and e to the negative t times e to the negative t gives me e to the negative 2t, right? So I can actually factor this down into e to the power of 2t plus, or e to the power of t. Where is it? Yeah, e to the power of t plus e to the power of negative t squared. All right. So I can actually factor this down to this. And that would be the same thing as e to the power of t plus e negative t. And so that's the magnitude of R prime t. And so actually integrating and finding the length of this, be integrating from 0 to 2 of e to the power of t plus e to the power of negative t times dt, right? And that's the same thing as e to the t minus e to the negative t from a lower bound of 0 and 2. So evaluating this, we get e to the power of 2 minus e to the negative 2. And that's going to be subtracted by 1 minus 1, right? Because e to the power of 0 is just 1. So we get e to the power of 2 minus 1 over e squared. Okay. Yeah, so that's an example of finding a length of the curve. All right. Okay. Now let's go and look at arc length functions. So another thing covered in 13.3 is arc length functions. Yeah. So arc length functions is basically, I would consider the same thing as finding length of curve, but you're finding a function instead of actually computing it. So that's why in the textbook, you'll see something like s of t is equal to the integral from a to t of r prime u times du. Right, so this is again using the same idea of finding a length of a arc or a curve, but you're trying to find the function of the arc length. Okay, so let's actually look at an example. It'll probably be more clear when I go through an example. So let's go through number 13. So for 13, they give us that r of t, or r of u, rather r of u, is equal to 5 minus u I hat plus 4u minus 3 j hat plus 3u k hat, and it gives us a point p4, 1, 3. And we're trying to find the arc length function of r of u, or whatever is given to us. Okay. All right, so let's see. So first of all, yeah, another thing they actually mentioned in the question, if I actually look at the question real quick. Yeah, it tells us to find the arc length function for the curve from the point P in the direction of increasing t. So you're not necessarily starting from the origin in this case, but you're starting from this point P right here. Okay, so this is basically a starting point for this question. Okay, so let's look at this. So again, same procedure, find R prime U. And R prime U is going to be the same thing as what? Negative I hat plus 4J hat plus 3K hat, right? Now the magnitude of R prime U is actually going to be equal to the square root of 1 plus 16 plus 9. So the same thing as square root 26. Oh, okay, so we have no variable in this. All right, okay, so plugging back in, we have S of t, plugging back into this formula, we have S of t is equal to the integral of a to t of the square root of 26 times du. So let's look at the lower and the upper bounds of this integral. This a basically represents your starting point. Okay. And it has to be in terms of u, right? So going back to this question, I forgot to specify that u is actually squeezed in between a and t. So let's try and correlate how we find the value from u from this starting point p of 4, 1, 3. So we can say that the x component, which is 5 minus u, that has to be equal to 4, right? And since 5 minus u is equal to 4, u has to be equal to 1. And we can verify that with the y. So if we plug in u is equal to 1, we get 4 minus 3, which is 1. And plugging u into as 1, we get 3 times 1 is 3. Right? So that actually works out. All right, so in this case, my lower bound is going to be 1, and it goes up to t of the square root of 26 times du. All right, so integrating this, I get square root of 26t, and evaluating from 1 till t. So, square root of 26u. Right, so evaluating this, I get square root of 26t minus the square root of 26. And this represents your arc length function. Okay, so you can basically, so if I were to write this down, S of t is equal to square root of 26t minus square root of 26. This basically represents the distance from the starting point in terms of time. All right, there's actually a second part to this question. So let's continue with this question. So for B, the next thing it states is it wants us to find the point 4 units along the curve. All right, so essentially they give us a distance, right? What we notice about S of t is that what we notice about R is that, sorry, let me erase this real quick. So instead of a time actually being given, they give us a displacement, or a distance basically. What we can do is we can actually take in, so I was right, so take in the S of t function, which was S of t is equal to square root 26t minus square root 26. And we can actually rewrite this into a form where S is the variable you're looking into. So if I rewrite this, I get S plus square root of 26 all over square root of 26. Right, and this is an S. So what I can do with this function right here is I can go back to R of t, or R of u, and just basically plug that value in for t of when S is equal to 4. And so that will relate to the point along the curve from this function. So if I were to copy this down, so R of u is equal to, let's see, our view was 5 minus t I hat plus 4t minus 3 j hat plus 3t k hat. Right. Let's see, 4t. Okay. Right. What you're essentially doing is I'm plugging in t or plugging in s to figure out my t, or 5u, sorry. 5u. All right, so let's try and figure that out. So what we can do is we're basically plugging in, let's see, so 4 minus, or yeah, so it'll be 5, it'll be 5 minus s plus square root 26 all over square root 26 I hat plus 4 square root 26 over square root 26. Wait, sorry. Wait, I'm going to type on my work. All right, give me a minute for this one. All right, so I got t, let's see. So t of 4. Okay, wait, hold up. Let me see the question real quick. Yeah, all right. Yeah, okay, I have it typed down. I might have made a mistake previously, but what we're basically doing, we're just plugging in t of 4 into this equation right here. So let me just, it'll be 5 minus s. So s, I'm just going to represent this s first, so let's not confuse ourselves. So I'm just going to represent t of s. So it'll be s plus square root of 26 all over square root of 26 I hat plus 4 times s plus square root 26 all over square root 26 minus 3 j hat plus 3 times s plus square root 26 all over square root 26 k hat. Okay. So again, yeah, I think there might have been something wrong with my work, but yeah, going back to this idea, what we basically did was we rearranged this s of t in terms of time, right? So we're isolating time instead because we're given that distance of 4 units. So what we do is we plug in, after rewriting it in terms of time, plugging it back to the original equation, right? So we're given r of u, basically plugging back in, and we have this general equation right here. Right? After forming the general equation, what we can do is we can plug in when s is equal to 4. So it'll be the same thing as 5 minus 4 plus square root of 26 all over square root of 26 I hat plus 4 times 4 plus square root of 26 all over square root of 26 minus 3 j hat plus 3 times 4 plus square root of 26 all over square root of 26. Okay, and we can try and simplify this down. So let's see. Okay, that'll be 5 over square root of 26, so 5 square root of 26. So it'll be 4 plus 4 square root of 26 all over square root of 26 for I, right? Or negative 4, sorry, negative 4 I hat plus, let's see, 16 square root of 26. Yeah, all right, so that'll be square root of 26 all over square root of 26. So that will be 3 square root of 26, 4, so that'll be 16 plus square root of 26 all over square root of 26. All right, I'm just expanding it out. And the third will be 12 plus 3 square root 26, all over square root 26. Right? Okay, and that should be our answer for 13B. Okay. I'm sorry for the confusion. Okay, but does that make sense? Any questions? All right. And I think that basically wraps it up for 13.3. Are there any other things you guys want me to cover before we finish the session? Oh, yeah, something. Yep. All right. Perfect. All right. Thanks for tuning in. Again, sorry for the last question. But yeah, if the work should make sense. But yeah, okay. Thanks for tuning in, and I'll see you next week.